Now I want to take a look at the derivative of an exponential function. A couple of points to make here. Our book is Calculus Early Transcendentals, and the notion of early transcendentals is a matter of when does the author decide to handle functions like exponential functions and logs and inverse trig and stuff like that. And if they do it in Calc 1, then it's called early transcendentals. If they do it in Calc 2, then it's just sort of the old-fashioned way of doing it. Anyway, our book is Early Transcendentals, and we handle exponential functions here in Calc 1. I want to point out to note the difference between exponential functions and polynomial functions or power functions that look like this. Here in the power functions or polynomials, the variable is in the base and the exponent is a constant. When I'm talking exponential functions, it's the other way around. The base is a number. This is like 2 to the x or 7 to the x. The variable is in the exponent. That makes it an exponential function. Okay. And the rules that we have for taking derivatives are going to look very different, although the functions kind of look the same because this variable is in the base and because that variable is in the exponent. The derivative rule will be very different. They are different functions. Okay. So first of all here, or next of all, just graphically, if you remember what these exponential functions look like, let's say that this is 1 right here. A to any power, sorry, any number to the 0 power, take 7 to the 0 or 14 to the 0 or negative 2 to the 0, it doesn't matter, that's equal to 1. So every single one of these exponential functions passes through the point 0, 1. And in general, they look like this, or they look like this, right? Or they look like this, or maybe this. And depending on the base, they're either opening up faster or slower, or maybe they're going down. And the blue one here might be something like, y equals 2 to the x, where the red one might be something bigger, like y equals 3 to the x. Headed downhill, you have some fractions here, so maybe 1/3 to the x. Or in purple here, this might be, if I'm trying to just do the mirror image of that one, so this would be y equals 1/2 to the x. All of them pass through here. Actually, there's one other that generally exponential functions, when you see them, they'll say this is a to the x, where a is a positive number and not equal to 1. Well, I mean, why not equal to 1? And the reason not equal to 1 is not a good enough reason in my book. I would say that we should take this one, because if you look at y equals 1 to the x, y equals 1 to the x power, that's just 1 all the time. So it doesn't go uphill or downhill, it just stays flat, but it fits very nicely in this family, sort of right in the middle. If the base is bigger than 1, you've got increase on the right hand side. If the base is less than 1, you have decrease. And if the base is equal to 1, well, you don't have increase or decrease, it just stays flat. Everything we do for these other ones will also be true for 1 to the x, so I don't see any reason to throw it away. Okay. So here we go. They all pass through this point. They all have different slopes. They pass through that point too, right? So here we go. Let's start with f of x equals a to the x, and let's take the derivative using the definition. So I want to look at the limit. So f prime of x here is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Now that's just the definition. I haven't done anything yet. Let's apply my function to this, or apply this to my function, however you like to think of it. This is the limit as h goes to 0 of, so f of x plus h would be a to the x plus h minus f of x, that's just f of a all over h. And then, a little bit of algebra here. I notice that the a to the x plus h can be rewritten this way. The limit as h goes to 0. This is a to the x times a to the h, and I'll leave everything else alone. Little explanation, usually we go the other way. Usually we have two things multiplied together with the same base and we just add the exponents. Well, I'm just taking that backwards. Now I notice that I have an a to the x in both terms on the top, so I'll factor it out. The limit as h goes to 0. I've got the a to the x times a to the h minus 1 over h. And then I notice that this is the limit as h goes to 0. The a to the x here is essentially a constant with respect to that. And one of the properties of limits is that the limit of a constant times a function is the constant times the limit. So I can pull this out in front. Oops. A to the h minus 1 over h. So getting it all on one screen there, what I'm saying is the derivative of an exponential function, the derivative of a to the x, is a to the x times whatever this limit is. Now, notice this doesn't depend on x at this point, so this is just going to be some number. If I could only figure out what it was, and we'll see how we do that eventually. But the point is, the derivative of an exponential function is the exponential function times this constant, right? We just need to figure out what this constant is. And in particular, note f prime of 0 is a to the 0 times the limit as h goes to 0 of a to the h minus 1 over h. Right? And the a to the 0 is just 1, so this is just this limit as h goes to 0 of a to the h minus 1 over h. So whatever this limit is, whatever this limit is, it's the slope of the curve as you're passing through 0. So this is going to be different for each value of a, but you can see that each value of a is going to give you a different thing. 2 is going to be here, 3 is going to be there, 1/3 is going to be there, right? That all those slopes are different as you pass through the origin. Okay. So let's see if we can get an idea of what those are. If I go this way, yes. So what I've done here is I've typed in, instead of h, I'm using x. So I'm looking at a equals 2. I got 2 to the x minus 1 over x. So that's like the 2 to the h minus 1 over h. And the question is, what happens as x, or as h gets close to 0? So as x gets close to 0 here. Well, I see that the value is about 1.6, almost 1.7 if I were to zoom in on that. I can see it's 1.6, maybe 1.69-ish. How far can I zoom in? Well, I can probably keep going, but yeah, it's 1.69. 1.693. Yeah, anyway, 1.693-ish, a little more than that. So the result is there. So if I have f of x equals 2 to the x, then the derivative, f prime of x, is 2 to the x times 0.693-ish, right? That the derivative of a to the x is a to the x times whatever this limit is. Well, for 2, the limit was this. Okay? And for each value of a, I'm going to have to figure out this limit. Well, eventually I'll have an easier way of figuring this out. But take a look at some other ones. What if I did 3 to the x instead? So let's go back over here and change this function from a 2 to a 3. Save that. And now look at the graph. Where is it now? Zoomed in too far. Oh, there it is. So now we've got a value in about the 1.1 range, it looks like. 1.109, 1.1098 something. Okay. So looking back here, if I look at the derivative of 3 to the x, I'm going to use the other notation just to get used to it. That's going to be 3 to the x times whatever that limit was, 1.098 something, right? Wouldn't it be cool if that number was 1? Because then you'd have a derivative of a function just equals itself times 1. Well, if I go back up here and I look at all these functions, they each have a different slope as I go in, and this one was 2 to the x apparently had a slope of 0.68 something, and 3 to the x had a slope of 1.1 there. Maybe somewhere in between 2 and 3 I can get one with exactly slope 1 as it passes through. And it turns out that you can. There's one number, and we actually make a definition. Definition. Let a number, and I'll call it e, be the number such that the limit as h goes to 0 of e to the h minus 1 over h equals, not 0, equals 1. Right? Now you may think you know what the number e is. You may have seen it before as the base of the common law, the natural log system. Well, it is the same e. In fact, if I go back to the graph here and say I don't want this, I want to see what I can do instead of 3. Let's take another number and see if we can get this to be at 1. So I'm going to zoom out a little bit here. Or zoom out a lot. There we go. Now I can see 1. So I'm going to go back to my equations here and say, well, how about 2? Oops. What if I say 2.5? Right? Save, draw the graph. Okay, now my limit is less than 1. So let me go back in here and say, no, not 2.5. How about 2.7 maybe? And then I say save, draw the graph. All right, now, yeah, the limit as h goes to 0. Now it's getting closer to 1. 2.7, I got to go a little bigger than 2.7, so maybe 2.7, 2. Save it. Give me the graph. Ooh, that was better. 2.72. Nope, that's a little bit too big. A little bit too big, so let's go back in here and say 2.7. Oh, maybe 2.71828, something like that. Save that. Draw the graph. And, that's going to be really close to 1 because I'm getting very close. So the thing is, the number e, which is the number you've known before, is a very nice number when it comes to derivatives. The derivative of e to the x with respect to x is e to the x times 1, so it's just e to the x. This function is the derivative of itself. That means that at any point, I'm almost out of time here, but at any point on the graph of y equals e to the x, right? Here's x. The y value right there is the same as the slope. So the bigger the y value, the bigger the slope. The smaller the y value, the smaller the slope. Notice that the y values are always positive, and this is always headed uphill. The slopes are always positive. Right here, at x equals 0, the y value is 1. The slope is 1. All right. There you go. There's the derivative of exponential functions with the star being e to the x. The derivative of e to the x is e to the x.